All right, so in this next section, we're going to start looking at volume. So there's a couple of different methods, different approaches that we can use to find volume. So we've seen with the integral that one of the major applications of a definite integral is to be finding the area underneath a curve. We're going to extend that now to look at the volume of a three-dimensional figure, okay? So if you look at each of these, you could determine each of these images, like what a cross-section of that would look like, what a flat piece of that would look like. And then we'll see a little bit more as we go what that's going to look like. So what we're going to do is we're going to rotate it around some axis. It might be the X, it might be the Y, it may be a different line completely. We're going to rotate around, say, Y equals 2. That is going to be called the axis of revolution. And then the resulting figure is going to be called the solid of revolution, okay? So just think about, for example, if we look at this rectangle here, what we would get if we were to take this rectangle and rotate it around the x-axis. And you would get this disc right here, that what you see. You can see here is the cross-section of that rectangle, but if we flip that around the graph, kind of like a flag, if you were to twist it all the way around, as this rectangle rotates around, we end up building this disc, okay? So this is how we extend this into volume. Now think about back just from geometry, when you find, say, the volume of a cylinder, okay? The way that we do this, you were already kind of thinking of this idea of accumulating area like we've talked about. So the area formula for a cylinder is you take the area of the base, which is pi r squared, and we multiply that by the height. So you're taking like that slice of area that's on the bottom and stacking it over the course of the height. That is exactly the approach that we are going to take when we look at volume, is we're going to look at these individual discs, and if I were to keep adding discs all the way across as I go, all of these discs, we're going to come up with an approximation of the volume of that figure. So since volume is equal to pi r squared, then we also need to multiply that by delta x, which is going to be your change over the course, like from point A to point B, wherever it is your interval is that you're looking at. And so we could set this up as a summation just the way that we did with integrals. And what we want is we want this delta x to approach 0, which would mean that the number of rectangles is approaching infinity, just like it did with area. Okay, so let's look at this and see if we can make a little bit more sense here. So let's say this is my from A to B, and I have my delta x here, which is the width of my rectangle. Now, this is just looking at one representative rectangle, but remember, we're going to have rectangles that go all the way across this region, and they may not all be the same width. It doesn't really matter. But we're going to have all of these rectangles that we're going to do as many as we can squeeze over this in that period. So that's what our delta x is we're looking at the width of that particular region. And so what this is going to look like, I have this on, let's see here. This is the figure that we're looking at. Okay, so this is this guy right here, this right there. So what this is going to look like as a solid is if we rotate this, we're literally going to spin this around the y-axis. Now let me kind of angle this here so you can sort of see what's happening. This is when it is, when it's flat, and then we're going to take this flat surface and rotate it around the x-axis, creating this solid that looks kind of like a funnel or a cone or something like that, okay? Now, when we look at this in terms of our rectangles, okay, if we look at this with the discs, Now we're going to have all of these rectangles, okay? And you can see, I'm going to try to not rotate them quite so far. I just want to see. There we go. Ugh, this thing has a mind of its own. But you can see here's a whole bunch of rectangles. Now, when we take the integral, we're going to get those rectangles to approach infinity. But now you can see that we have all of these different rectangles here. It looks kind of like this. That's a better view. And now as I rotate here, we are going to get all of these different discs as we go around. You can sort of see I have all of these little cylinders now stacked on top of each other. And if you look kind of at a cross section here, that's sort of what we see is happening. So when we take these integrals and when we do this accumulation of volume, you're basically adding up all of those little tiny discs of volume to create the volume of the entire figure. Okay, so this would be a small number of discs. This is just one. And so if we refer to this as a representative rectangle, then we will refer to the disc as the representative disc. Okay, so when all of this is said and done, we know that the volume of a disc is pi r squared times the width. We're talking width because this is horizontal. It could be height if we're talking vertical. Okay. And so the way that we're going to figure this out is we kind of translate this into calculus. This would be where we take our summation, but we know that we can translate these summations even nicer into an integral. And so the way this will work is this is basically the volume formula for a cylinder. Pi r squared times the height. Taking the integral from a to b, that determines the width of your figure, and then we have all of these discs as we go across that we want to add up. That's going to go from a to b. So the integral takes care of the width piece. Pi r squared gives you the area of each of those discs, and then we're going to add all of those together by taking the integral. So here is a basic, succinct summary of what the disc method is. So notice that it changes whether we're doing respect to x or respect to y, depending on which axis we are going to rotate about. So if it is a horizontal axis of revolution, then we're going to integrate with respect to x. If it is a vertical axis of revolution, we're going to integrate with respect to y. So if we were going with respect to x, okay, those are the examples that we just looked at. I would take my sort of representative rectangle here, and I would rotate it around the x-axis, so we would end up with these discs. Okay, now if I was doing this with respect to y, that would be a little bit different. We might be taking a rectangle here and rotating it about the y-axis here for just a second. Marty's being a grump. I'm sorry, he's making noise. So we'd get these discs that look like that, and I know I'm not the best artist, but that's the idea, is which direction we're rotating. With respect to x, we're going around the x-axis like this. With respect to y, we'd be going around the y-axis like this, okay? So one thing to notice about the disc method, because like I said, this is just one of the methods that we're going to be looking at when it comes to volume. One of the things to make sure you notice about the disc method is that the representative rectangle that you are rotating in each of these instances is perpendicular to the axis of revolution. So I have this rectangle here that makes a right angle with the axis of revolution. If I had a horizontal rectangle like this, it is perpendicular to the y-axis, so that is how the disc method sort of works, okay? Now, one of the big questions here is how to figure out the radius. If the axis of revolution is just the x-axis or the y-axis, then the radius is just going to be f of x or f of y. If it's not, then we might have to think this through just a little bit more, and that is what we'll look at in example 2. So let's look at an example here. We want to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis from 0 to pi. And we want to rotate that, so we're bounded by this graph, by the x-axis, so here's our region. And now we want to rotate that around the x-axis, and we're going to obtain this solid of revolution. It kind of looks like a little like silly putty egg or something. So here is, let's see, is this the right one? No. Here is this image, just to kind of really work on trying to visualize what we're doing here again. So I'm going to put this at a little bit of an angle. When we rotate this, we're going to basically take that and rotate it all the way around the y-axis, and we're going to obtain this solid. Now again, if you want to think about what this integral is really doing, is we're taking all of these discs and we're adding more and more and more discs, making them as skinny as we can to find the area of all of these little discs that we're going to chop this solid into, and then add all of those areas up by taking the definite integral, okay? So what we have to remember, this all comes down to that volume is equal to pi r squared times the width. Width because we're going horizontally here, okay? So we know that this is with respect to the x-axis. So our volume is going to be pi times the integral from a to b, which in this case is 0 to pi, of r of x squared. We want the radius, whatever that function ends up being, dx. Okay, so now we have to decide what r of x is. And why is pi on the outside? Well, really we're taking the integral of pi r squared like this, but since pi is a constant, that's why we get to bring it out to the front. So that's why we just pull that outside of our integral there. Okay, so the radius, hopefully it kind of makes sense that that is going to be the height of our representative rectangle here. Well, that value r of x, in this case, because it's the height from the x-axis, that is just f of x. So in this case, r of x is equal to f of x, because that's going to give us the y value there. And for this function, r of x is equal to the square root of sine of x. Okay, so it's just the same way as when we did like the width delta x times the height. And the height, if we were to just do the integral here, the height would be the y value that we're trying to figure out from that particular area. So that's why it's just the function itself, f of x. So we can take that and plug that into our integral here. So the volume is going to be pi times the antiderivative from 0 to pi of the square root of the sine of x squared dx. And you can see this one is actually going to work out pretty nicely. When we square the square root of sine of x, we're just going to get the integral from 0 to pi of sine of x dx. That comes out to pi times negative cosine of x from 0 to pi. When we evaluate that, the cosine at pi is -1 times a negative makes it +1 minus the cosine at 0, which is +1, but then it's going to flip negative here. And so we get that the volume is 2 pi. So the volume of that surface that we create is 2 pi. If we just took the integral of the square root of sine of x, we would not be getting volume, we'd be getting the area of this flat surface right here. But when we do the pi r squared and then integrate it, we're finding the volume of all of those discs if we were to go left to right. So the process here is really not that difficult. It's really just kind of this wrapping your brain around what is happening and like visually what's going on, that is a little bit challenging here, okay? I want to look at one more example today and then we'll kind of pick up where we left off when I see you next. But example 2 here. This one is a little bit different. So I want to look at how determining the radius might become a little bit different if I am rotating around an axis that is not necessarily a coordinate axis, like the x-axis or the y-axis. So we're going to go horizontal again here today. We'll talk about with respect to y tomorrow or Monday. So, okay, so we want to find the volume of the solid formed by revolving this region bounded by the graphs of f of x equals 2 minus x squared, g of x equals 1, and we want to rotate about the line y equals 1. So instead of rotating like we were doing before, instead of rotating this around the x-axis, we're instead looking at this line y equals 1, and this is where we're going to make our rotation. So again, just to help you kind of see what it is that we're doing, this is what that graph looks like, okay? We can add the discs onto here, and you can see if I move this just a hair, like here's where our discs are, okay? So we've got all of these discs, and again, we're trying to squeeze infinitely many of these on there. That's why we're taking the integral. So when we rotate, it's going to rotate around, and again, the x-axis is down here at the bottom. Sorry, I just realized you can't see the cursor on here when I'm moving it, but the x-axis is at the bottom of the screen. We're like a unit above the x-axis. And so when we rotate this, we get this odd-looking little solid with all of these discs that we've chopped it up into. Now, we can take the discs out here and see what this looks like smooth. So we get this kind of funny shape that comes to a point on either side. This is what we want to find the volume of. Now, the power of being able to integrate this is not a figure that we have a formula for. We don't know how to find the area of this weird wonky thing, and so we can use integration to be able to come up with that, okay? So we're going about the x-axis again. So we're going to use the exact same volume formula. This time we are going to be going from -1 to +1 because that's where it intersects with the line g of x equals 1. So we're going from -1 to +1 of, whoops, I forgot my pi. Don't forget that. I'm bad about that. R of x squared dx. So the question here that we really have to think about is, what is r of x? How are we going to determine the radius? Okay, so to figure out this point right here, that would be f of x, because that is where we land on the curve. Now this curve, remember, in reality probably keeps going, whatever, but this blue region is all that we're worried about. So we want this value here. But what is interesting about that, and this is kind of like when we find the area between two curves, okay, if I'm looking at this graph that looks like this, okay, this point right here is f of x. So that would be the distance from here to here. But what is different about what we're looking at is we have this line y equals 1, and we don't want this distance to be part of our radius. So if that is the line y equals 1, then we need to subtract that. This is just like what we did in section 1.1. The top curve would be f of x, the bottom curve would be g of x. And so to determine the value of r of x, in this case, our radius equation, we are going to have to do f of x minus g of x, which is going to come out to 2 minus x squared minus 1, because again, we want to take away this extra piece here that we don't want to be part of our radius. And so this is going to come out to 1 minus x squared for r of x. So now we're ready to go ahead and bring this down. The volume is going to be equal to pi times the integral from -1 to 1 of 1 minus x squared dx. So this gives us pi times x minus x cubed over 3 from -1 to 1. And you can work this out in your calculator. We're going to have, let's see, 1 minus 1/3 minus -1 plus 1/3. So this is going to be 2/3 plus 2/3. So we end up with 4 pi thirds for the volume of that particular region. Okay, so you've got some homework that you can start working on tonight. We'll pick up where we left off on Monday, and feel free to email me. I will see you guys soon.